Hello everyone. I am Rita van der Walt, and I am presenting my research on the diagnostics of indoor environmental quality exposures and climate infrastructure vulnerability in South African schools for the Doctor of Philosophy. The Western Cape faces a critical infrastructure budget deficit. Budget cuts and the increased demand for school placement has forced something called the Rapid School Build Program, which is a program by the Education Department to deploy prefab classrooms to meet immediate needs. However, this creates this infrastructure trilemma that we see here. The constraint of low cost and rollout speed forces a sacrifice in environmental quality. These units are deployed without climate adaptation, so they are very cold in winter and they overheat in summer. So given grid stability and running costs, active HVAC or active heating or cooling is not scalable, so we need passive and targeted interventions to improve free running conditions. This creates a real-world problem, which is an unregulated health risk. Learners in these classrooms are exposed to thermal stress and poor air quality that impairs cognition. This adds to educational inequity that we already see in the Western Cape specifically. Yet, because these exposures are unmonitored, they remain invisible and are overlooked. This reveals the research problem, the diagnostic gap. We have a policy vacuum because we have an evidence vacuum. You cannot fix a problem that you do not understand. Even though Sustainable Development Goals and National Development Plans prioritize infrastructure, the lack of data means that these classrooms cannot be audited. Together, these two problems form the core challenge of the dissertation: to make the invisible problem visible by quantifying exposures and therefore environmental inequity, and to transform the raw data into actionable engineering criteria for retrofit and policy. To bridge this gap, my primary research question focuses on three engineering objectives: to use IoT sensing to solve the data scarcity, use observational analysis to quantify exposures and risk, and develop model-agnostic diagnostics to derive building physics without metadata. The ultimate goal from this is to quantify climate infrastructure vulnerability and inequity, specifically to inform retrofit policy. From this, we derive the following research question: is how can we integrate IoT sensing, observational analysis, and model-agnostic diagnostics to quantify climate infrastructure vulnerability and inform retrofit policy? To answer this, I developed a 5-stage methodological framework. It flows from the engineering layer, which entails sensing and data collection, to data configuration, including data cleaning and bias reduction, into the observational layer to answer the question, what are conditions in these classrooms like? The diagnostic layer to identify the drivers of the observed conditions, and finally the application layer, which includes the implications for policy and standards recommendations. So I will begin with the engineering design. To analyze multiple schools simultaneously, I designed these custom sensing nodes. I prioritized spatial resolution over laboratory-grade precision equipment, accepting the known trade-offs of low-cost sensors to gain network scale. I monitored indoor air parameters specifically identified to affect school children most in terms of their comfort, health, and cognitive ability. In each classroom, I measured temperature and relative humidity, which affect thermal sensation and thermal comfort, carbon dioxide, which affects cognition even at levels below discomfort, but also acts as a proxy for the room's ventilation, and particulate matter of 3 different sizes, which poses a respiratory health risk. Every sensing device also had a battery backup to ensure data continuity during power outages or load shedding. The deployment covered 6 different classroom types, which I split into permanent and temporary classroom infrastructure. For the permanent classrooms, I captured the differences between ground floor and top floor brick classrooms in a 2-story building, as well as single-story brick classrooms. For temporary classrooms, we explicitly need to distinguish between containers, which are repurposed shipping units, and prefabricated mobiles, which are purpose-built classrooms. This distinction is critical as they are often considered the same under the umbrella term temporary. However, the results show that they have vastly different physical characteristics and indoor thermal performance and are therefore not the same. We also include a case study of a container classroom with a low-cost retrofit. This classroom has wood panels on its north and south-facing walls to test the efficacy of both the framework and of low-cost interventions. Sensor data without context is just noise, so to maximize the utility of the data set, I enriched the time series measurements with 4 high-resolution metadata layers. This included physical attributes like building materials, dimensions, orientation, and construction information for each room. The Stellenbosch microclimate was captured with historical 5-minute weather data for the full data collection period. Occupancy schedules, which took into account the day of week, school calendars, daily school schedules, and detailed information, which led to 31 unique occupancy schedules mapped to each unique room and date. Finally, I obtained historical electrical availability, capturing both planned and unplanned electrical outages. This data was directly obtained from a designated company which measures municipal electrical availability. This metadata of the electrical availability allows us to distinguish on whether HVAC methods were available for use or not. The data collection yielded 2.8 million measurement vectors. However, the real-world setup imposed unique challenges like unplugged sensors, internal heating, or other sensor artifacts. I implemented a strict data cleaning protocol, retaining but flagging raw data for transparency in the published dataset, but these data points were removed entirely for the observational analysis to preserve result integrity. To ensure the statistical validity across uneven sample sizes, I utilized a hierarchical linear weighted mean aggregation function. So rather than a simple mean, this algorithm aggregates first by device, then by room, and then by classroom type for each 10-minute interval to prevent rooms with higher sensor counts from skewing the classroom type averages. The success of this aggregation is shown in this histogram. Despite raw data imbalances as sample sizes increased, we achieve a stable measurement density which is equally weighted across seasons that was used for class type and temporal observational analysis. So moving to the observational analysis, which answers the question on what the indoor air environment is like and what exposure levels were. Temporary classrooms we see here in the warm colors are not only hotter and colder than permanent classrooms, but also more volatile. This volatility is a physical signature of a building with a low thermal mass. In the field, I noticed that on very hot days, specifically teachers from the container classrooms would resort to moving lessons outside under trees rather than remaining indoors, even though air conditioning was running on full blast. This highlights the severity of indoor temperatures in those container classrooms. The disparity between temporary and permanent infrastructure classrooms is also quantifiable. When we consider the total range of measured temperatures for the two classroom types, or for the two classroom categories, the range for temporary classrooms is 13 degrees Celsius wider than that of the brick classrooms. This confirms that temporary structures do not buffer the external climate, but actually amplifies it. But thermal comfort is not only based on what temperatures our bodies are exposed to, but actually also determined by the rate of change of these temperatures. The ASHRAE 55 standard specifies limits for indoor temperature swings or thermal drifts. For example, we can see here 1.7 degrees Celsius change in 30 minutes or 2.2 degrees Celsius in an hour to prevent thermal discomfort. Here we analyze what percentage of school days exceeded these limits during teaching hours. So in brick classrooms, we see some exceedances of the respective limits, but these numbers are notably higher for temporary infrastructure classrooms. If we highlight the cases where more than 50% of school days exceed these limits in teaching time, we see that this is exclusively in the temporary infrastructure classrooms and for nearly all cases. These classrooms therefore fluctuate indoor temperature too rapidly for learners and teachers to physiologically adapt without experiencing thermal discomfort. Moving to carbon dioxide, which is our indicator for a classroom ventilation. Here we see how average CO2 rises during lesson times and it falls during break times over a school day. The steepness of this decay that we see during break times represents a room's natural ventilation potential. In many cases, this flush out of CO2 is too slow to reset the air quality before the next occupancy period, leading to elevated CO2 levels. When we compare the measured CO2 levels between container and prefab classroom, which both use air conditioning for HVAC, we see statistically significantly higher CO2 levels in container classrooms than in prefab classrooms. This is attributed to a design failure. Container classrooms are effectively sealed boxes, so during the retrofit stage to classrooms, cross-ventilation was likely not sufficiently prioritized. Considering HVAC type, counterintuitively, brick classrooms equipped with a combination of ceiling fans but also air conditioning have statistically significantly higher levels of CO2 than those only with ceiling fans. This reveals a behavioral driver. To keep conditioned air in and to preserve electricity, teachers and students tend to keep windows shut during aircon use. This hampers ventilation. This indicates that without passive design for natural ventilation, but also indoor temperatures, occupants purchase thermal comfort at the cost of air quality. This phenomenon of active coping causing pollutant buildups is not unique to schools. It's a universal human response to infrastructure failure and thermal vulnerability. To validate this mechanism, we must look at where else this happens, at home. Just like teachers close windows to stay cool in summer, households burn wood to stay warm in winter. In both cases, the building envelope fails and the human reaction creates an indoor air quality challenge. Thermal discomfort is therefore not only a nuisance, but it actually drives behavior that actively degrades air quality. To validate that this is a universal mechanism of climate infrastructure vulnerability and not just a school-specific anomaly of active coping, we transition from schools to living rooms by monitoring amenity fireplace use in winter. This is a residential equivalent of closed windows, occupants intervening to fix a thermal deficit. Note the logarithmic scale here. Both open and enclosed fireplaces drive PM2.5 24-hour exposure levels several orders of magnitude above World Health Organization safety guidelines of 15 micrograms per cubic meter. This graph actually mirrors the CO2 accumulation that we just saw in schools. It's the same closed box phenomenon, but just with a different pollutant. This confirms a universal theme in infrastructure failure. When the building envelope fails to provide passive thermal comfort, occupants intervene, creating a secondary air quality crisis. In schools, it's the carbon dioxide exposure due to window closing, and in households, it's the particulate matter exposure from wood combustion. This creates a compounding risk scenario. Occupants are simultaneously exposed to thermal stress and respiratory irritants, amplifying the health burden on vulnerable groups like children. So back to school classrooms, having quantified the symptoms of thermal volatility and pollutant buildup, we now require the diagnosis and the causal analysis to isolate what the drivers are of these observed indoor temperatures. I characterized climate infrastructure vulnerability under free running conditions by performing sensitivity analysis with indoor temperatures as the output and historical weather data as inputs. Standard correlation or variance-based sensitivity analysis fails here because the influence of weather is nonlinear, time-delayed, and highly autocorrelated in time series. Therefore, I selected the delta moment independent measure, DMIM. This is a distribution-based method of global sensitivity analysis. Simply put, this method is based on the principle of looking at how much the distribution of indoor temperature shifts when a specific weather parameter changes. It allows us to derive physics from data. It is model agnostic, and it works purely from measured indoor temperatures without any reliance on building information as other simulation software requires. This method returns a delta score, with higher scores indicating greater sensitivity to that weather parameter. However, I identified a limitation in the standard SALib Python library implementation. It assumes that input data is uniformly distributed, but real weather and real-world data is not uniform. We consider precipitation rate as an example. Precipitation rate, as we can see here, was 0 for more than 75% of the data set. The standard bootstrap subset selection for sensitivity analysis ignores this, but this means that most of the samples used to calculate the importance of precipitation rate will be based on samples with 0 precipitation. This falsely suppresses its sensitivity result. To solve this, I developed a bias-aware bootstrap subsampling technique. This forces the bootstrap subset to consider two cases. First, a binary approach, which I named STEP, telling us what is the sensitivity to whether it rains or not, regardless of how much it rained. For this, 50% of the bootstrap consists of zeros, and the other 50% consists of the non-zero values binned across the non-zero distribution. The second case, named the balanced case, says what is the sensitivity to precipitation. Here, the bootstrap subset is equally binned over the full distribution of the input feature to calculate its sensitivity. We see the effect of this enhancement in the resulting delta score, where it is suppressed with the old bootstrap method, but notably higher for the STEP and balanced methods respectively. Now, this allows us to compare results among weather parameters, even when they have different distributions or different natures of influence on indoor temperatures. This enhancement to Bootstrap sample selection is not only for this dissertation. My code was peer-reviewed and merged into SALib, which is the global open source Python library for sensitivity analysis, and it is now available to use by engineers and researchers globally, enabling them to, for the first time, accurately perform DMIM on real-world data sets. I applied this corrected algorithm to the 12 hours of weather preceding a measurement. This creates a temporal sensitivity profile for each weather parameter, meaning that we can for the first time derive time series sensitivity metrics like the time of greatest influence and the sensitivity sharpness. The size of the maximum delta score tells us how strongly the indoor temperature responds to a weather parameter. We use this as a proxy for thermal resistance, and this indicates the building's insulation. By considering the duration of the peak magnitude, we can see how sustained this indoor temperature reaction is. This is a proxy for thermal capacitance and is an indicator of the building's thermal mass. These metrics also allow for more specific retrofits insights rather than general recommendations like increase the insulation or increase the thermal mass. For example, I found that prefabs have notably higher sensitivity to precipitation rates specifically than other roof-exposed buildings do. This identifies the prefab's classroom's roof as its key infrastructure vulnerability. Therefore, we can recommend specifically roof insulation, and it's not necessary to insulate the entire room. This enables lower cost but effective interventions. That is the power of this tool. It moves from a general problem to a specific retrofit recommendation, making it optimal for applying targeted and low-cost interventions effectively without requiring any building information or complex modeling software. A big challenge is to make these results interpretable for policy. So what I did is I mapped the derived thermal capacitance and thermal resistance proxies on an RC quadrant. On the x-axis, we have resistance, which relates to the building's insulation, and on the y-axis, we have thermal capacitance, which relates to thermal mass. The goal here is the bottom left quadrant, where we have high thermal resistance and high thermal capacitance. In this quadrant, buildings will have a slow and weak indoor temperature response to weather parameters. The two roof-exposed brick buildings have very similar performance, with the second-story brick classroom benefiting from the added thermal mass below it from the first story. The first-floor brick building has the highest resistance and thermal capacitance and is the best performer when it comes to climate resilience. However, when we consider the temporary infrastructure, we see that they have severely worse thermal resistance and thermal capacitance properties. These results also reflect the temperature extremes and the volatile trajectories that we saw in the observational analysis. The container classroom being the worst performer can also add to the elevated CO2 levels that were measured, as windows may be kept shut for longer durations of time due to the increased thermal vulnerability. But does this tool work for retrofit verification? When we consider the container retrofit case, we see that the adding of wood panels has a substantial thermal resistance benefit, so insulation benefit. But because the thermal mass of the container classroom was so low before the retrofit, the wood panels even slightly improved its thermal capacitance. This proves the framework's utility. It maps the building's genetic code without any model or simulation information, diagnoses failures, but it also characterizes the success of a retrofit. Something that's also valuable to note here is that because we don't use any simulation or building data and only work from the measured indoor temperatures, this RC framework doesn't exclusively describe the physical building. It identifies climate vulnerabilities in the exact setup as the classroom currently stands, therefore accounting for other physical factors which may impact the indoor temperature as well. For example, partial shading from trees or another building, which would have been incredibly complex to accurately model or simulate. This makes this framework incredibly valuable for low-cost and case-specific diagnostics to decide on targeted retrofits. Moving to the application layer, my findings expose a critical regulatory gap. Currently, the label temporary is used as a loophole to bypass energy efficiency compliance with the standard SENS 10400XA. My first recommendation is the elimination of this temporary label. A low-cost classroom used as a long-term solution is permanent, and these classrooms must be subjected to the same thermal performance and energy use mandates as brick buildings do. Second, standards must be revisited to be practically enforceable. The current South African regulations, SANS 10400O, specify ventilation rate requirements in liter per second per person. This is unenforceable and no inspector can measure air flux as is. We need a shift to performance-based standards, as in most international standards, which typically recommends CO2 levels below 1,000 ppm, something that is measurable and enforceable. My third recommendation is a shift towards child-centric and classroom-specific standards for the indoor environment. This is the norm in the United Kingdom and the European Union with their Building Bulletin 101 and in Australia with their national construction codes. Children are physiologically more vulnerable than adults, and our regulations must reflect that. Finally, I recommend a factory-first approach to the Rapid School Build program and their prefab classroom rollouts. We cannot fix these units efficiently after deployment. Policy must mandate pre-deployment verification of thermal properties with specific consideration for the deployment climate context and apply and test retrofits before they deliver them. The application of my findings and this framework to the relevant building and indoor air quality standards and codes will directly contribute towards the developmental goals outlined in the National Development Plan for 2030, specifically environmental sustainability and equitable infrastructure objectives, the Department of Science, Technology and Innovation's Decadal Plan, including their objectives pertaining to global change, society and sustainability, and the Department of Health's strategic goals for safe and sustainable learning environments. By characterizing the link between infrastructure and respiratory risk, we reframe retrofits in terms of the United Nations Sustainable Development Goals and the South African shift towards them. Retrofits are not only infrastructure spending relating to Goal 11, but they are simultaneously a preventative health intervention for Goal 3 and act as an educational equity intervention for quality education, United Nations Goal 4. In conclusion, this dissertation delivers contributions across 4 dimensions. I established the first longitudinal indoor environmental quality dataset for South African schools. This consisted of 2.8 million data points to form a baseline for future evidence. This made a substantial empirical contribution and it addresses the data scarcity vacuum. This includes a published data paper and the open source dataset. The invisible problem was made visible by my diagnostic contribution, where I quantified exposures and provided the first evidence quantifying the environmental inequity among classroom types. Importantly, I highlighted a link between infrastructure thermal resilience and air quality degradation due to occupant coping. This resulted in 2 publications. The development of real-world tools for real-world data and the interpretable findings made a methodological contribution. The bias-corrected bootstrap for sensitivity analysis and the time series RC mapping framework to infer building physics purely from indoor temperatures carry substantial methodological value in the form of an open source software contribution and an article. Finally, the societal contribution. I operationalized a data to policy framework and I translated technical diagnostics into managerial guidelines that align directly with the National Development Plan and the United Nations Sustainable Development Goals for local government. This contribution manifested as policy engagement and managerial conclusions and recommendations for policy and stakeholders towards sustainable development. These contributions are validated, published, and in use. The hard outputs include 4 journal articles, of which 3 are already published, the full 24-month dataset, which is cleaned, documented, and published as open access, my bias correction algorithm, which has been peer-reviewed and merged into EssayLib. It is now available globally. And findings were presented by invitation to the City of Cape Town, where I directly participated in and influenced local health policy discussions. Public dissemination articles for platforms like The Conversation are also currently being drafted to ensure that these findings reach the broader public. This work provides a baseline of indoor air environmental exposures, as well as a scalable diagnostic tool for classroom climate infrastructure vulnerabilities in the Western Cape climate. This framework can be extended beyond classrooms for sustainable cities and communities in diverse climates. My work demonstrated that through scalable sensing and novel data diagnostics, we can protect learner health and learning potential, even in resource-constrained environments. Thank you.
Great. Thank you very much, Ms. van der Walt. Thank you for your presentation. We're going to move on to questions from the public audience.